Introductions to Mathematical Statistics. Today we'll continue with the solution of exercises on the probability set section, and that's question 1.3. So in our last video we stopped at question number 12. So we continue from question number 13. So here's question number 13. We have three distinct integers are chosen at random from the first 20 positive integer. We have to compute the probability that their sum is even, their product is even. Alright. So we know that for us to have that A, when their sum is even. So what are the conditions for us to have sum in even of a first 20 positive integer? We know that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So for us to have a sum that will be even, that means that we first case 1, that means that the three integers we are going to add must be an even numbers, which is like, for example, 2 plus 4, 6 plus 6, that will be 12. So that means that the three distinct integers are even. Let's just say 3 even. So if a sum of 3 even integers, then we are going to have a sum that will be even. However, I think there is still another way whereby we can get sum of 3 integers that's going to give us even. So another case now is that if we sum up 2 odd and 1 even, that is 1 plus 3, 4, 4 plus 2, 6, 3 plus 5, 5 plus 3, 8, and then 8 plus n. So that means that we can have 2 odd and then 1 even. So I don't that those are the two possible way, I believe. So with that now the probability of A which sum is even will be equals to the first case, that will be selecting 3 even from positive integers. So the total number of positive integer we have is this is just 10, we are going to 20. So let me complete this: 11, 12, 13, 14, 15, 16, 17, 18. Let me write this. So this will guide us 17, 18, 19, 20. So we have 10 even numbers. So out of 10 even number, we pick 3. And then case 2, we have to pick 2 odd, and we have 10 odd integer, then we pick 2, and that is multiplication 1 even. We have 10 even, and then we picked 1 over 20 integer, then we picked 3. So you can work on that. So and then you can verify that the result is 570 over 1140, and that's equals to half. Okay, so the second question, I want to push this down so that I can solve this second question here also. push this here. So the second question, their product is even. Their product, that is their multiplication, is even. So what are the cases? So case 1, for us to have a product that is even, so let's go. So if you multiply 2 times 4, 6, 6 times 6, 36. That means that if all the 3 integers are even, then their product also will be even. That's case 1. Case 2 is, what if we pick 2 evens number? That's 2 times 4, 6, 6 times 3, 18. Then 2 even, 1 odd also is going to give us a product. So that means that we pick 2 even and then 1 odd. So what other case? Let's check if we pick all 3 odd. 1 times 3, 3 times 5, 15. So if we pick odd, the product also will be odd. So that doesn't work. But if we pick 2 odd and 1 even, what about that? That 1 times 3, 3 times 2, 6. That's worked fine. So we have 2 odds and 1 even. So we have 3 cases. So another way whereby you can actually solve this is to say that the probability of B is equal to 1 minus probability that their product is odd. And for us to get an odd product, we just need one case, which is that the 3 integers are odd. And for us to pick 3 integers that are odd from the first 20 positive integers, we know that we have 10 of them, then we pick 3 over the favorable outcome 20, or total outcome 20 over 3. So that's another way. You can go through these cases, or you just go through one cases, and then you have your result. And that, if you solve that carefully, you're going to have 1 minus 1 over 9, which is equal to 5 over 9. And that completes that question. So the next question number 14. 14. Yeah. There are 5 red sheeps and 3 blue sheeps in a bowl. The red sheeps are numbered 1 to 5 respectively, and the blue sheeps are numbered 1 to 3 respectively. If 2 sheeps are to be drawn at random and without replacement, we have to find the probability that these sheeps have either the same number or the same color. So let's see, we have 1 red sheep, 1, 2, 3, 4, 5. Then blue, we have 1, 2, 3. So our total outcome so how many sheeps do we have altogether? We have 8, and out of those 8 we want to pick how many? Just there are 5 red, we have to pick how many? 2 sheeps. So we have 8 combination 2. So now we have to pick either the same number, or the same color. So to pick the same number, the sheep have the same number. So for us to pick the same number, that means that we just have 3 cases. That is 1, 2, 3. right? We have this. So that means that we have three ships that have the same number, right? And then we pick two. So the same color, that means that we can pick from the red, or we pick from the blue. So the probability of everything together, let's denote our event to be what? Let me see if I can copy this. So I don't think that's possible then. I'm just select A, same number, event of same number, or the same color. So probability of A now equals to the addition of all the cases we have, which is 3 combination 2, that is same color or same number, of our total outcome, which is 8 combination 2. So if you also solve this carefully, then you have 16 over 28, and if you take that to the lowest term, you have 4 over 7. So you can also verify that, and that complete that question. The next question number 15. So here's question number 15. In a lot of 50 light bulbs, there are 2 bad bulbs. An inspector examines 5 bulbs which are selected at random and without replacement. So let's make that our total outcome. So we have 50 light bulb, then we picked 5 out of it. So we have to find the probability of at least one defect bulb among the 5. So probability of at least one defective bulb. Let me just take that. Let A, event of at least one defective bulb among the 5. And let B be non-defective bulb among the 5. So with that, so probability of A, the probability at least one defective bulb among the 5, can easily compute it by the complementary. That will be 1 minus probability that there is none defective. So, and then if there will not be any defective, then it means that these 2 bad bulbs, you have to subtract it from the 50 bulbs, and that gives us 48. So we have 48 total numbers of light bulbs that are not defective. Then out of it we picked how many? And expected examine 5 bulbs. So we pick 5 bulbs out of it, and then we take our 50 combination 5, which is the total outcome. Then if we compute this, we are going to have numerically because this is huge. So you're going to have approximately 0.19818. Okay, so that is that. So the next question, let me push this here. So the next question, how many bulbs should be examined so that the probability of finding at least one bad bulb exceed 1/2? So following the same, so we don't know the number of bulb to examine, so we have probability of A equals to 1 minus probability of B. But here now I want to look for 1 minus 48 combination N, which is the number of bulb to be examined, over 50 combination N, the number of bulb to be examined, so that their result of finding at least one bad bulb will exceed 1/2. So 1/2, and then we can simplify this by having 1 minus half greater than 48 combination N, 50 combination N. Then we have half, so we can just switch this 48 combination N over 50 combination N should be less than 1/2. So you can just solve iteratively by checking N equals to 5, N equals to 10, and see if the result will be less than 0.5. Or the more you increase it, N equals to 15. That is the easier ways to actually check. So if you check carefully, you know that the minimum number of bulb to be examined so that their result will be less than half is N equals to 15. So you can verify that at your end. So the next question is next question, we're going to check question number 17. Question number 17. So we have if C1 CK are events in the sample space, to show that the probability that at least one of the events occur is 1 minus probability that none of them occur. So another one, probability of C1 union union CK, that equals to 1 minus probability of no one of them occur, and that is, so let's use this theorem. We know that probability of A complement is equals to 1 minus probability of A. So that means that we have to put complement here. So this is equals to complement of this is equals to 1 minus probability of C1 okay, so probability of C1 union union CK. So by De Morgan's law, we have this to be probability of C1 intersection complement intersection dot intersection ck complement, and then equals 1 minus probability of C1 union dot union ck. So then if we shift it around, you see the probability C1 dot ck is equals to 1 minus probability of C1 complement intersection dot intersection ckc. So we take this here, then we take this back here, then you have that result. So the key here is the use of De Morgan's law. Then you're done. So question number 18. So here's question number 18. Yeah, a secretary types 3 letters and the 3 corresponding envelopes. In a hurry, he places at random 1 letter in each envelope. So what is the probability that at least 1 letter is in the correct envelope? So we are given a hint that here be the event that the ith letter is in the correct envelope. So we have to expand this to determine the probability. So by inclusion and exclusion law, inclusion and exclusion law, we have this the probability of C1 plus probability of C2 plus probability of C3 minus probability of C1 intersection C2 and probability of C2 intersection C3 minus probability of C1 intersection C3 plus probability of C1 intersection C2 intersection C3. Alright, so we have 3 letters. So we are going to permutate over 6. Okay, so the probability of C1 occurring, that is probability that he put it into the right envelope. He put letter C2 in the right envelope, letter C3 in the R envelope, is because we only have 1 letters, only have probability of 1/3. Then the probability that C1 enter into the right envelope is because he has only 1 right envelope. Then the probability of C1 and probability of C2 and probability of C3 is equal to 1/3. So why probability of C1 and C2 and probability of C2 and C3, probability of C1 and C3. So that is probability that the secretary puts the right letter C1 and the right letter into the right envelope, letter C2. So if C1 is correct, C2 is correct, definitely C2 also will be correct, right? And that means that we also have 1/6 cases of this, because we have 3 random way to permute that cases. So then lastly, the probability that C1 is correct, C2 is correct, and C3 is correct is just 1/6 possible way in order to put in the letters. So substitute all these values. So we substitute all this value here. So that means that the probability of C1 union C2 union C3 equals to 1/3 minus 1/6 minus 1/6 minus 1/6 plus 1/6. So you can carefully undo this fraction. Then this should be equal to 1 minus 1/3, which is equal to 2/3. and that gives us the right answer. So the probability that at least one letter is placed in the correct envelope is 2/3. Okay, so let's move to the next question. That's problem 19. Problem 19. We have considered the poker hands drawn from a well shuffled deck as described in our previous example. We have to determine the probability of a full house. A full house means 3 of one kind and 2 of another kind. So we know we have 13 kinds and we have 4 suits, and then we have 552 number of cards. So now the probability of our poker's hand drawn of a full house, probability of full house is equals to, so we have 3 of one kind. That means that we, from 13 kinds we pick one kind, and after that one kind we pick 3 of suit, or and 2 of another kind. So we pick 13 out of this, 14 out of this. Then we also now pick, so we have 12 kinds left. Out of those 12 kinds we have to pick 2 of another. We pick out of those kinds, then we pick 4/2. So you can carefully examine how we pick our cases again so that you will understand it much more better. So that is, we have 13 kinds, and then 30 kinds. Let's say we have in a playing card, for example, we have 0, we have A, we stand for 1, we have 2, 3, 4, 5, 6, 7, 8, 9, then J, K, Q, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we have 4 types of this. So these are what we call kinds. So we also have, maybe this is for diamond, then this is for art. So we also have the same kind of this set. So then we also have the same for spade. And for spade, then we also have the same for shade. So this is for so we also have this. So then we pick 13. First of all, so when we make the same kind, then we make either we have 0, 0, 0, 0, or A, or 2, 2, 2, 2, 2, 2. So that means that we first of all pick a kind, and we have 13 kinds. So out of 13 kinds, we pick 3. For example, maybe we pick zeros. So out of 0, we just pick 3. We have 4 possible zeros, but we only pick 3. So if assuming that this is what we pick, then we are left with 12 kinds. Out of those 12 kinds also, we just need 1 and 1, 2 of another. So then we have 4 of this, then out of 4 we just pick 2 out of that. So and our total outcome is 52 combination 5. Then if you also solve that carefully, you have something which number 3744 over 259 8960. And if you approximate it, this is about 0.00144 0.00144. So that is that. So the next question that is interesting, question number 22, and that will be the last question we're going to check. Then our next video we go to conditional probability. So consider the events C1, C2, C3, and suppose they are mutually exclusive events. That means that the intersection of any of these sets are 0. So if probability of C1 is equal to P1 for each A1, so we have to find the restrictions on the sum of these P1, P2 plus P3, and we have to solve question number 2 and B of it. So first, question A, we have pick C1 equals to P1, PC2 equals to P2, and PC3 equals to P3. Okay, so then if you take their union, probability of C1 union C2 union C3, since they are mutually disjoint, will be equal to probability of C1 plus C2 plus C3, and then this is P1 plus P2 plus P3, and this should be less than or equals to 1. And then we also know that our probability must always greater than 0. So probability of P1 plus P2 plus P3 also must be greater than 0. So the restriction of this is P1 plus P2 plus P3 must be in between 1, and they must be greater than 0, in between 0 and 1. So that is the restriction for that. For B, you have if P1 equals to 4 over 10, and P2 is equals to 3 over 10, and P3 equals to 5 over 10, we have to verify if these events are actually mutually exclusive. So our P1 plus P2 plus P3 equals to 4 plus 3 plus 5 over 10, and that is equals to 12 over 10, and that is equals to 1.2, and that is not equals to 1. So since they are not equals to 1, P1 or C1, C3 are not mutually, C1, C2 and C3 are not mutually exclusive. And that completes that result. Okay, so here we stop for some solution for this exercise. So in our next video we check conditional probability and independence. So hope to see you in the next video. Thank you.